So far, we have always described polytopes as the intersection of finitely many half-spaces, and this follows directly from the definition of polytopes. In this video, we will see a different way to represent polytopes, namely as the convex hull of a finite number of vectors. The first thing we need is the definition of convex combination and of convex hull. So let's say that we're considering k vectors in Rn that we denote by x1 until xk. And then we also have k scalars lambda 1, lambda k in R. We assume that all the lambda i's are non-negative and that they sum to 1. Then the vector sum over all i's from 1 to k of lambda I times xi is said to be a convex combination of the vectors x1 until xk. Furthermore, the convex hull of x1 until xk is the set of all the convex combinations of x1 until xk. If k is equal to 2, we only have two vectors, let's say this x1 and x2, so let's ignore the other ones in this picture for now. In this case, you will only have lambda 1 and lambda 2, and since they sum to 1, lambda 2 will be exactly equal to lambda 1 minus 1. And so we have already seen an example of a convex combination of two vectors. In fact, we have seen this in the definition of extreme point. Using the definition of convex combination, we can now reformulate the definition of extreme point, and so we can say that a vector x in P is an extreme point of P if x is not a convex combination of two vectors in P. So if you have only two vectors, x1 and x2, the convex hull of x1 and x2 is exactly the segment joining them. If you consider all the 7 vectors in this picture, then the convex hull that you obtain is this pentagon, which is the smallest convex set containing all these points. So far, we have always been thinking about polyhedra as the intersection of finitely many half-spaces. In the next theorem, we see that they can also be described in terms of convex hulls. A non-empty polytope is the convex hull of its extreme points. The first thing to notice is that we're not considering all polyhedra here. In fact, we need to have polytopes, so bounded polyhedra, and of course we need non-emptiness. We will not prove this theorem, and if you're interested in the proof, I suggest you look at the textbook. On the other hand, soon we will prove a theorem which can be seen as a converse of theorem 2.9. In fact, we will see that the convex hull of a finite number of points is always a polyhedron. So for now, instead of proving these results, I just want to give you a few examples so that you can get your hands dirty with these two different representations of polytopes. Let's consider, for example, the polytope P in R3, described by non-negativity constraints and x1 plus x2 plus x3 less than or equal to 1. This is the polytope highlighted in gray in the picture above, and it has 4 extreme points, namely the origin, the vector 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now how can we check these two different types of representation? Well, one direction is to pick any vector in P and check that it can be written as a convex combination of the 4 extreme points. So for example, let's pick the vector 1/3, 1/3, 1/4. This vector belongs to P. To convince yourself, well, you immediately see that all the components are non-negative, so the non-negative constraints are satisfied, and then if you plug in 1/3, 1/3, 1/4, you will see that the sum is less than or equal to 1. So this vector belongs to P, and we should be able to write it as a convex combination of the 4 extreme points. So what we have to do is find the 4 lambdas corresponding to the 4 extreme points. You can check that the lambdas are given by 1/4 for the vector 0, 0, 1, 1/3 for the extreme point 1, 0, 0, 1/3 for the extreme point 0, 1, 0, and 1/12 for the vector 0, 0, 0. So what do we need to check at this point? We need to check first that this is a convex combination, and in order to do that, you only need to check that the lambdas are all non-negative, which they are, and that they sum to 1. And if you check, they do. Finally, you need to check that this sum actually gives you our vector x, which is 1/3, 1/3, 1/4. And it should be, if I didn't make any mistake. So next, let's see the opposite direction, namely, let's pick any convex combination of these four extreme points, and we check that the convex combination is indeed in P, therefore it satisfies all the constraints defining P. So in this case, we start from the lambdas. We just need to pick any four lambdas that sum to 1 and that are non-negative. We can pick, for example, 1/3, 1/6, 1/6, and 1/3. Now we compute the convex combination, which is the vector 1/6, 1/6, 1/3, and you can now check that it actually belongs to P because it satisfies all the constraints. This concludes this short video. In the next video, we will prove that the convex hull of finitely many points is a polyhedron, and we will see what is perhaps the oldest method to solve linear programming problems.